All right. Um, so we're going to be taking relations, mapping, and function. Now we're going to be beginning with relations. All right. Now, you see, relations encompass both mapping and function. Is that okay? So more like the big guy, the superset is relations. Is that okay? And the subset, mapping and function. Exactly. Okay, so relations simply means the connection. Think of it as relationship. Is that okay? The connection between two sets. Usually we use two sets. Is that okay? So the connection between two sets. For example, we can have a set of maybe animals, and I say something like, let's say um, I have a dog here, and I have a she goat here, and I have a what again? I could have um, a hen. Yes, thank you. Okay. Basically this, and then I have a cock, a she goat, and a bitch. All right. So, and you're asked to match them. Okay. So you match dog with what? With bitch. She goes with what? Hen with cock. Is that okay? But of course, if I had chicken here, which one would you match with chicken? Hen, right? Now, basically, the relation here, or the connection between dog and bitch, is that one is a male, the other is female. She goat, female, male. Hen, male, female. But the relation between hen and chicken is that the other is what? Living. This one is cooked, right? Non living. Do you understand? So the relation changes here. But basically, it's showing you this thing, this connection. It's showing you that, or this diagram is showing you that there is a connection between these two. That is why we match them up. Is that okay? And there are different types of relation. We have one-to-one relation, one-to-one relation. Now, one-to-one relation is the one in which I I have the two sets. So let's call them sets A and set B. So on the values here, say 1, 2, 3, 4, and here maybe A, B, C, D. So if I match this to this, this to this, this to this, and this to this. Now this is a one-to-one mapping. Why? Because every guy here is matched to only one guy here. Is that okay? I'm using the word match for now. Is that okay? Because there's mapping. Mapping is quite different from relations, but mapping is inside relations. Is that okay? Now, this guy here, where we are mapping from, is called the domain. It's called what? And this guy here that we are mapping to is called what? Do you remember? Codomain. It's called what? The codomain. Now, all of these elements here, each individual element here, that these guys are mapped onto, that is, these guys that are in the domain are matched with. The guys individually are called the image. So, for example, if I asked you what is the image of 2 in B, it will be what? A. The image of 3 in B will be what? C. So we call it image. The guys that, think of them as the guys that represent them in the other side. Is that okay? In the codomain. All right. Then we now have what is called range. Now you see, the range is the set of all the guys here that has been mapped to or matched. So if a guy here is not matched, the guy is not part of the range. Is that okay? So the range here is going to be, because it's a set, we use the curly brackets too. So we have A, B, C, D, Y, because all of these guys here are matched. Is that okay? But given that, for example, this guy is not matched, for example, matched, and this guy is matched with this guy. So 3 is matched with D, 1 is matched with the same guy D. Is that okay? So that in that case, the range will be A, B without C and D. Does that make sense? Is it clear? All right. Now this type will no longer be a one-to-one, because here it is not one element that is matched with one element here throughout. So in a case here, we have like 2 elements that are matched to 1 here, right? So this will be called many to 1. Is that okay? Just because there is at least 2 that are matched to 1 or matched with 1. Is that okay? So in that case, we call it many to 1. But if we now have something like this, where we have 1, 2, 3, 4, for example, and we have A, B, C, D. And then we have something like this. Now in this case, there is still, this is still a relation. Is that okay? This is a relation. Why? Because there's a connection. Once there is a connection between those 2 sets, it's a relation. Is that okay? Now, what set the relation might now differ? I'm going to show you something soon. Now, you see, in this case, this will be called a 1. What would you call this? If you call this many to 1, what would you call this one? Yes, 1 is mapped to many here. Even though there are guys here that are 1 to 1, 1 to 1. But as far as there is 1 here that is mapped to many, it means this or matched with many, this relation has become what? 1 to many relation, okay? Now there is also a case where we have something like this. Let's see, use our values 1, 2, 3, A, B, C, for example. In this case, you could have something like this, something like this, something like this, something like this, something like this. In this case, what do you think you call this? This will still be many to many, yes. This will be many to many. Does this make sense? Is it clear to us? Why is it many to many? Because more than one guy is here have two guys, two values that are mapped to here. Is that clear? Okay. Okay. So because in this case, B is mapped, 2 is mapped to B or matched with B, and 1 is matched with B. So that's many here. And of course, 1 and 2 are mapping to A and B and C. So that's many to many. So those are the different types of relations that we can have. We have 1 to 1, many to 1, 1 to many, and many to many. Those are the types of relation. But when it comes to mapping, with mapping, our scope is quite restricted. Is that okay? Now, in mapping, we cannot have, the only conditions we can have is this, that at least one guy here, at least all the guys here first must be mapped to something. Is that okay? All the guys here must be mapped to something. If there is a case where this guy, there is a guy here that is not mapped, then it is not mapping. It is only a relation, but not what? Mapping. Is that one clear? Okay, so for example, this example here is not mapping. Is that okay? Now, another thing that is not mapping is this. When we have many, when we have 1 to many, that case too is not mapping. That case is not what? It's not mapping. So mapping has to do with when we have 1 to 1 and 1 many to 1. Is it 1 to many? Yeah, many to 1, yes. So this can be, these two are the only types of mapping we have, but not this guy. Is that okay? 1 to 1 and many to 1. Okay. Now, it is also possible that in our mapping, that some guy here is not mapped to. So this case is also a mapping. Why? Because all the guys here has been mapped to something. Once it has been mapped to something, it is mapping. Once a value in the domain is a member of the domain has been mapped, has an image in the codomain, then it is what? Mapping. But if there is a guy in the domain that doesn't have an image in the codomain, then it is not what? It is not mapping. Or when one guy, one member of the domain has many elements, many images in the codomain, it is what? Not mapping to. Do we understand? All right. Now there is something called rule of mapping. Rule of mapping. Now, rule of mapping is just what sets a mapping. So, for example, this relationship that we are setting here, we could set it with numbers. For example, let's set it with numbers. And I have something like, 2, minus 2, 3, and minus 3. And then I have 4, 9 here. And then you now have something like this. This goes to this, as well as this goes to this. This goes to this, as well as this goes to this. Now, the mechanism that brings this value to this place, let's say this was set y, set x, set y. The mechanism that brings a member of the domain, domain x, to a member of the codomain, an image, or that gives a member of the domain an image. That mechanism is called a rule. It's called a what? When I was probably introducing one of you to it, I said you could think of it as a machine. That what you put in here, you're going to put something in that machine and then to produce something out for you. Do you understand? Okay, so it's the same way here. It's called the rule that gives every member of the domain an image in the codomain. Is that clear? Now, what is the rule here for what you're seeing? So let's call the rule, let's call it F, for example. Let's call it F, for example. So if we call it F, now, F always transforms every value that is inside this domain X. It always transforms into a value in domain Y. Now, how do you think it's transforming here? How do you think 2 is becoming 4 and minus 2 is still becoming 4 here? You don't know? Well, how do you think I can turn 2 to 4 and still turn minus 2 the same way to 4? By square it. No, I say by square it. By squaring it. Do you understand? So if I square these guys, so it means that the rule of this mapping is going to be what? X squared. Is that clear now? So by squaring each of these guys, so the rule of the mapping is that an equation that brings a member, that gives a member of the domain an image in the co-domain. Is that clear? Are we good with that? So I said the two types of mapping that we can have are one-to-one mapping and many-to-one mapping. Now, when does mapping become a function? Now, mapping becomes a function when it basically deals with only numbers. Is that okay? So this is still a mapping. This is still a mapping because it follows the rule. There is one-to-one and many-to-one. Is that okay? In this case. So it's still a mapping. And why is it a mapping? Because it follows these two rules. But it is not a function because it doesn't comprise of only numbers. Do you understand now? So when it comprises of numbers alone, they are functions. Are we good with that? So the rule that controls them is called function of the domain. The rule that we set. So for example now, in this case, the rule that controls this value, this relationship is going to be what? F of x. Is that okay? So f of x here is going to be what? X squared. Do we understand now? So if I want to generate a value if I impute a new value here, say 5 for example, and I wanted to generate a new value for it, what would I do? I'll just plug in this value 5 into my rule. So when I plug it in, what do I get? 5 squared, which is what? 25. And it turns out that whether it's positive or negative 5, I plug into it, I'll get what? And which is what? Many to 1. Is that okay? All right. So those are the types of relationships. Now let's go on to functions. Let's continue to functions. Now the types of function, the major types of function, or would I say the 2 types of function? There are actually 3. One-to-one mapping, one-to-one function, and no, so there are two. One-to-one and many-to-one. Is that okay? Now we also have what is called, now a mapping can also be onto and into. A mapping can also be what? Onto and into. Now, on that basis, we classify them into 3, which are the injective mapping, the injective function, and the surjective function, and the bijective function. Is that okay? Now, when is a function injective? Now, when is function injective? A function is injective if every domain, if at least an image in the codomain is mapped to by one from the domain. Is that okay? Now, then when is this subjective? I'm going to give you the examples here. Is that okay? When is this subjective? It is subjective when every guy in the domain, when every guy in the codomain is mapped onto. When every guy in the codomain is what? Mapped onto. That is every guy in the codomain is an image in the domain. Once there is a guy such as we have here, that is not an image of something here, this mapping is no longer surjective. Is that okay? Now, when is the mapping now bijective? It is bijective when it is one-to-one and onto. This is what I mean by one-to-one and onto. Onto means every guy in the domain has been mapped to. Does that make sense? Every guy in the codomain has been what? Mapped to. So this is what I mean by onto. For example, if I have 2, 4, 3 here, and I have 4, I have 6, 3, 9 here, for example. Now, if I link this to this, link this to this, and link this to this. Now, this mapping is one-to-one. Did you get that? Okay. Now, this mapping is one-to-one, and is also completely mapped to. Every guy is completely mapped to every guy here, isn't it? And it is one-to-one, right? So this kind of mapping is said to be onto because every guy in the domain, in the codomain, has been mapped to. Is that clear? Okay. So in this case, this is a bijective case. Is that okay? Why is it bijective? Because it is one-to-one and everybody is mapped to. One-to-one and onto is called what? Bijective. Now, but look at this guy. If I have 2, 3, 4, 5, and I have 6, 7, 8, 9 here, for example. And I have this. This guy is mapped to this. This guy is mapped to this. This guy is mapped to this. The same guy is mapped to this. Now look at this. First, is this an onto mapping? Why is it not onto? Because it's not everything here that is mapped onto, right? Good. Now is this guy one-to-one? Is it one-to-one? No, right? Now, if it were one-to-one throughout, it could have been what? It could have been now what is? There are two okay, this will not be a mapping if I took this from here. But let's say I added another value here, for example. I added another value here. And I took this value to 8. This would be a surjective mapping. Why? Why is it subjective? Everybody here is mapped to everybody here. Does that make sense? You know bijective. Everybody here is mapped to everybody here, but it is 1 to 1. Here, it doesn't have to be 1 to 1. Are you listening to me? All we have to do in this case is just make sure that everybody here is mapped with everybody here. But it doesn't have to be 1 to 1. It is when it's 1 to 1 and everybody is mapped onto, that is what? Bijective. Is that one clear? So in this case, this is called what? Surjective. But look at this case, where we have 2, for example, 3, 4, 5, and 6, 7, 8, 9, for example. And we now have this guy mapped to this guy mapped to the same guy, this guy mapped to this guy mapped to this guy, which was the first example I showed you the other time. Now in this case, we have, now, let's say for example I have something like this. Let me add one more here, like 10 for example. Let me add 10 here. Now look at this case. This is 1 to 1. Is that okay? But is this subjective? It's not subjective. Is this bijective? No. Is it? Now, in this case, if there was no guy here, if there was a guy here that was not mapped, this would not be a mapping, you remember? But in this case, where there is a guy here that is not mapped to, this is still a mapping. If there is a guy in the codomain that is not mapped to, it's still what? A mapping. But now, in this case, we have only 1 to 1, even though not everybody is mapped to. This is called injective. This is called what? Injective. Are you sure you're clear? Good. So for subjective, we can have many to 1. For subjective, the only idea is that in subjective, everybody in the codomain must be mapped onto. So if that is the case, therefore, then it will be subjective. But a subjective can be a bijective, in the sense that now this guy now is bijective only because it is 1 to 1 and everybody is what? Mapped. Does that make sense? Now, this case is subjective and not bijective because there is a guy here that is being mapped to by 2 guys. If it were just single guys mapped to one guy, it would have been what? Bijective. Is it clear to us? Okay. So that's the condition for injective, subjective, and bijective. So this is bijective. Okay. All right. So now let's now talk about the different types. So we've talked about bijective. There's still what we call composite or composite function. Is it composite or composite? Composite. So what's a composite function? So a composite function is just a function in which, for example, I have a relation like this. Let's say I have 1, 2, 3, 4 that maps to 5, 6, 7. And each of these are now mapped again to say 8, 9, 10. The relation is weird, though, but this is just an example. Is that okay? This is just an example. Now, let's call this y x, let's call this y, let's call this z. So let's say the rule that brings every value of x to y is called f. And the rule that brings every value of y to z, let's call it g. This case is going to be a composite function. It's going to be what? Composite function, because when you say something is composite, what does it mean? It means it has different uses, right? The composite here just talks about the fact that there is more than one part. Is that okay? In the mapping, okay? So in this case, if I say, give me f of 2, for example, what would be the image of 2? 6, right? But what if I said, give me give me G of F of 2? That would what? 8. Does that make sense? Now, how did we get F of 2 first? F of 2 means, what did this rule turn 2 into? The rule turned 2 to 6, or mapped 2 to 6. So we have this. Now in this case, this one is asking you to use this rule, the second rule, to turn F of 2 to something. So F of 2, F turned 2 into what? To 6 already. So G will now turn that 6 into what? 8. Does that make sense? Okay. Now let's now treat real cases before we do what is called. Then the last type of function we'll look at is the inverse function. Then we'll end it with the types of graph. I hope you remember the types of graph. Did you graph them? Okay, didn't even remind me to give you the question. Okay, so what did I say? So yeah, no, the examples of composite function that you're likely to see. So you see something like this, that a particular function f of x is equal to x squared plus 1, and g of x is 2x minus 1 or 2x minus 3. Let's use a good number. And let's say maybe h of x is given as x plus 2, for example. So these whole things are simple, right? Okay, so if you are told to find, you could be told to find f of, now there are two ways we can write it. Is that right? Fg of 2, for example, or I write something like this, f of g of 2. Is that okay? We put a not here. Is that okay? All right. So either as you see it, they mean the same thing. What this value simply means is that first plug the value, these two, into the G machine. So whatever G changes it to, you now plug that one into the F machine. Does that make sense? Okay. So where is the G machine? We know that G of x is given by what? 2x minus 3. So we have 2x minus 3. So from here, G of 2 will now be what? 2 into bracket 2 minus 3, isn't it? There from here we have this times this what? 4 minus 3. So this becomes what? 1. Now, f of that thing is now f of what? F of 1. So that what? F of 1, which is what? Remember that f of x is this squared plus 1. That what? 1 squared plus 1, which is what? 2. Is that clear? Is it hard at all? Very simple, right? So give me the value for h of g of f of minus 3. Everybody fast, fastest finger, of minus half. H of g of f of minus 1. First, let's take f of minus 1. Since we know that f of x is this squared plus 1, that's what? Minus 1 squared plus 1. That becomes minus 1 over 4, because minus will disappear, right? Plus 1. That becomes 1 over 4. So we'll now plug this value. We'll plug it into we'll plug this value. Now, there are two ways of approaching this question. Is that okay? There are two ways. I'm going to show you the second way. We'll now plug that value into G, the G machine. So G machine is 2x minus 3. So G of this will now be G of 1 over 4. That will be 2 times, this is 5 over 4, right? Minus 3, isn't it? So it becomes 2.5. Hey, minus 3 is equal to minus half. So h of 3. You will show me 3. So h of x is what? X plus 2 here. So h of that whole value will be h of minus half, which is what? Minus 1 over 2 plus 2, which is what? 1 and half. Is this clear? All right. The other way to go about this is this. Listen, since we are plugging in the value of f into g and that of g and f into h, we could do it this way too. We could go by the functions alone first. Then we'll plug our value into the function that we generate. See what I mean here? You can go by, since we already know f to be this, so this whole value, we'll plug it into g first. So it will become g of x squared plus 1. Does that make sense? So that will be 2 into bracket x squared plus 1 minus 3. This will become 2x squared plus 2 minus 3. So that what? 2x squared plus 1. Is this clear? So this whole value will now plug into minus 1. Thank you. So this whole value will now plug into this guy. Does that make sense? So h of g of x squared plus 1 will now be equal to what? H is x plus 2, right? So that will become 2x squared minus 1 plus 2. This becomes 2x squared minus 3 minus 1 plus 2. This will become plus 1, right? 2x squared plus 1. Is this clear? So let's now plug in our value, the value of minus half into this. So h of all of that of minus half will now be what? 2 times 1 over 2 squared. That's 1 over 4, right? Am I wrong or right? Plus 1. 2 here 1, 2 here 2. And that becomes 1 plus half, 1 and half. You see it's the same thing. Okay. So that's how to go about it. So now is it clear? Okay. So now let's go to the inverse function. Inverse function. So we're still going to maintain those functions. Now what's an inverse function? An inverse function is simply what? A reverse function. An inverse function is simply what? A reverse function. Okay, so for example, if we have g of x, let me start with a simple one. G of x is 2x minus 3. So g of inverse function of g of x will be written like this: g raised to power minus 1 of x. It is read like this: g inverse of x. Does that make sense? This way we write it, we read it as g inverse of x. Okay? So what do you do here? It's very simple. You simply make x the subject of the formula. So how do you do that? Bring this guy here, becomes g of x plus 3 is equal to what? 2x. Then you now divide both sides by 2. So when you divide both sides by 2, x is going to what? G of x plus 3 over 2. Now because it's the inverse you are trying to make, you are going to change this x to g inverse of x and change this place to x. That becomes x plus 3 over 2. One idea with inverse function is that it always reverses the function. For example, what would g of 2 give me? G of 2 would give me what? 2 into bracket 2 minus 3, that would what? 1, right? Okay. Now, what would g inverse of 2 give me? Let's see. G inverse of 2 will be 2 plus 3 over 2. What would this be? That would be 2 and half, isn't it? So, and that's supposed to be inverse of what? It doesn't prove anything here, right? It doesn't. But the point is that the inverse function always reverses it. So another way to do it is this. You can make that g of x, make it become y, for example, a single letter that you can reckon with. So y will become 2x minus 3. The same idea, you bring this guy here, becomes y plus 3 is equal to what? 2x. Then you now divide both sides by 2. So x will now equal to what? Y plus 3 over 2. So what will now happen is this. This x will become the g inverse of x. But here, where you see y here, will now become what? X plus 3 over 2. So you see the idea is the same. Are we good? So who can, without touching the book, give me f inverse of x? What will it be? F inverse of x from that function. I'm not going to force it on. F inverse of x will be what?
X minus 1.
With x minus 1. Are you sure? Let's see. Since f inverse of x is x squared plus 1. So in this case, x squared will be equal to f of x minus 1. So you take square root of both sides. So you are correct. And then x, which will now be f inverse of x, will now be equal to what? Square root of x minus 1. That's good. Is it clear? Okay. Now, using our former examples, what if you are now asked to find something like this? H inverse of G H inverse of G of F inverse of minus 3. What if we are told to find something like this? It's very simple, isn't it? Now, the first thing you have to check for is, do I have my inverse H function and do I have my inverse F function? If you don't, you first create them. Is that okay? So your inverse F function has been created here, right? So F inverse of x, recall, is root x minus 1. Then H inverse function, we don't have it yet. So what would that be? X minus 2. Is that clear? Yes, that's correct. So let's create F inverse of minus 3 will now give us what? That will be F inverse of minus 3 will be equal to square root of 3 minus 1. That is root 2. Does that make sense? So we now plug root 2 into G. That becomes G of root 2. Does that make sense? Did I lose anyone? Good. So we have equal to 2 into bracket root 2 minus 3. So this becomes, what's that? Our x is, minus 3, sorry. Minus 3. So minus 3 minus that. That will be root minus 4. Right? Somebody say right. we happen to have a complex number. So this will become the square root of minus 1 times 4. Does this make sense to us? This will become the square root of minus 1 times the square root of 4. Does this make sense? So this becomes 2, right? Now root 1 is designated I. So this becomes what? 2i. Does this make sense? So you now plug in 2i into what? Into G now. So recall that G of x is 2x minus 3. So that will be G of 2i. Does this make sense? That becomes 2 into like a 2i minus 3. This becomes what? 4i minus 3. Does this make sense? Okay. Now, we'll now plug in this whole thing into H inverse. Is it clear? Okay. Okay, so let's plug in that into H inverse. Recalling that H inverse of x is x minus 2. So we'll plug in that, but that becomes H inverse of 4i minus 3. This becomes what? 4i minus 3 minus 2. So that becomes what? 4i minus 5. And so that will be the answer. Is it clear? All right. So that is that for mapping, relations, mapping, and function. All right. Then the other thing you should now know are the standard functions that we have. Let's discuss the standard functions we have. Not all, I can't remember all now. Is that okay? So we'll just discuss the major ones that you will need for calculus. Is that okay? I'm supposed to write calculus on top so I will know that that's the series we are treating. Okay, so some standard functions, as I said. Okay, so we have a constant function, isn't it? Constant function k, right? So f of x could be equal to k. What will be the graph of f of x? The graph of f of x is going to look how? Like this, isn't it? A straight line, right? Okay. So that is that guy. You know that the straight line equation is like this: y equal to mx plus c. So you are going to see that it's going to have only an intercept, y-intercept, but it doesn't have a gradient. The gradient or slope is 0. Is it sloping? Is the line sloping? You see that? So that's why it's having this 0, so y equal to c. So that is, so if f of x was y equal to k or c. Does that make sense now? Okay, so this is the graph of the equation. Now what of a linear equation? A linear function rather. A linear function. How is that going to look like? To look like this. If it's forward progressive, right? Then if it's regressive, it could look like this, isn't it? Still linear, right? What's she doing? Yes, okay. No, you are just doing like what? All right, then how about now we also have a quadratic function, right? Hey, when we get to trig function, I'll really test you. So we could have a quadratic function. Our function could be quadratic. So if it's quadratic, what are we going to have? That is our f of x here. Here, f of x is equal to mx plus c. Here, f of x is going to be x squared, right? Plus other values. So in this case, what is it going to be? Sitting on x directly, right? Something like this, okay? Now, what of an inverse function? The graph of an inverse function. Say f of x equal to 1 over x. How would this look like? An inverse function. It's going to be what? Piecewise, thank you. So can you come and draw it piecewise? Do you remember piecewise? How? Piecewise. Yes, and the other will come. Piecewise. Okay, so it's going to have something like this and something like this, okay? All right. So how about, are we good? How about a square root function? If f of x were to be equal to square root of x, and if f of x, how about cubic? We did not even treat cubic. Cubic, x cube. How does x cube look like? No, that one is sine, I think. The sinusoidal. That's sine now. How will root x look like? I think root x is going to look like this. I can't remember. I think it's something like this. You have eaten with it. Shame on you. How about this guy? F of x is the cubic. How will the cubic look like? This one I can't even really remember. But I think it's something like this. Which function looks like this? No, there's tan. Oh, this is not tan. Oh. I think this cube. Is this cubic? Where is square? This is square, right? I think this is cubic. Yes. That's this cubic because remember inflection and then the rise. So that's cubic. You see? You people, Are we good? All right, let's get to trig functions now. Let's see how much you remember. So how does a sine graph look like? If f of x were sine x, how would it look like? Like this, right? Okay, so these are considering one wavelength. Okay, so this is sinusoidal, right? Okay, how about if f of x were cos x? How would that one look like? We're going to start from here, right? Okay. Like this, right? You know, sometimes we end it here too. So if you have a graph that just goes like this, it's also cosec too. Yeah? Sometimes it ends at pi over 2. Sometimes they can end it at pi over 2. They might not give you the full wavelength. In some cases, they'll give you the full wavelength. This is a full wavelength here, right? Okay, but basically, if you see a graph like this, so once it's starting from here, it's always out of phase with this guy with sine x by 90 degrees. Is that okay? And I told you they are just shifted versions of each other. If I bring this guy to the back, you see it's going to look like the sine graph again, isn't it? So more like we shifted the sine graph here. Is that clear? Okay. So who is lagging? Is this sine or cos? Sine is lagging, yes. Because by the time, no, this guy is lagging, cos is lagging. Because by the time this guy, who is lagging? By the time this guy gets here, this guy would have gotten to his maximum. Well, I think sine is lagging. Anyways, let's leave the laggers and the leaders. Let's get to the f of x for tan. Thank you. For tan x. Who can remember? Come on, Drake. Tan x is going to look like this. Like this, right? This one. Tan x is going to look no. It's going to go up. Yeah, something like this tan. Is this not tan? Tan is like cubic function, cubic graph. Only that cubic is closer to the y-axis. But here is between pi over 2 and pi over 2, that's 90 degrees. Is that okay? It's going to go to infinity here and to infinity here. Do you remember? See you guys here. So what will be the inverse of this? What's tan inverse? 1 over tan is what? Cot, right? So what will cot graph look like? If tan is floating on, it's very simple to make. It's floating like this. Then the inverse of that will be something like this. It's going to come and then it's going to be between pi over 2 here and pi over 2 here, negative pi over 2. Do you disagree? No, right? Okay. This is going to be cot. So like that. Cosec, how will cosec look like? Cosec is 1 over sec, right? 1 over sine rather. 1 over sine. Okay, so how would that be? If it's when you see, this is what I'll do. I'll send you a list, this thing. There was this thing that this man posted recently about the sign mathematics dance moves. You did not see that thing? I think I posted it. Okay, no, I didn't post it. I thought I sent it to our group. I'll send it to our group so you master all those graphs. Is that okay? Because even I've forgotten some of this. Is that clear? Yes, master all the graphs. You must know the function so that when you see the graph, you know this is because there are some relations in calculus now that will just tell you, we'll just give you the graph and then we'll tell you to evaluate something about it, and then all you have to know is what the graph actually stands for first. Do we understand? Do we understand? All right, so that will bring us to the end of the video. Do well to subscribe to the channel and click the bell notification. Then reach me on WhatsApp in case you need questions on this idea. God bless you as you subscribe and share the video with your friends.